Assalamualaikum class. So for today class we go to the AC circuit analysis. So AC circuit analysis is actually we do a analysis for the circuit, but now the input in a AC form, right? So analyzing AC circuit usually require three steps, right? The first one is we need to transform the circuit to Passer or frequency domain. So usually you are given the circuit in a time domain. So then you need to transform the circuit into a Passer domain. So if the circuit is already in a Passer domain, so you no need to transfer the circuit to transform the circuit. Second step is actually to solve the problem using any circuit technique, right? So when I say any circuit techniques, that means you can use nodal analysis, you can use mesh analysis, superposition, and whatever analysis that we did in DC analysis, so we can use also in AC circuit analysis. So the last steps, you need to transform the resulting Passer to the time domains. But this one is depends. Sometimes you need to transform into a time domain. Sometimes you just can leave your answer in a Passer form. Okay, we go to the source transformation technique. So in AC circuit analysis, we can do a nodal analysis, mesh analysis, source transformation, superposition, a northern Thevenin and Northern theorem. But we not go all of it. We just go some method in order for you to understand how we did analysis in how we analyze an AC circuit, right? So we go to the source transformation. So as you know, source transformation involves transforming a voltage source in series with an impedance to a current source uh, in parallel with an impedance or vice versa. Okay, so that's mean in a source transformation, you transform a voltage source that connected in series with impedance to a current source that connected in parallel with impedance. Okay, so therefore, if you see the diagram here, so this is how we did a source transformation. So the first one here is impedance in series with your voltage source, and then the second one here, the circuit is actually your current source in parallel with your impedance. So you can transform voltage source into a current source uh, and vice versa, but you must follow this rule, which is for voltage source uh, that can be transformed into a current source, the impedance must be in series, right? And then for current source to transform into a voltage source, so the impedance must be in parallel with the current source. So therefore the value of the current source and also a voltage source can be calculated using this formula. So you can find the value of Vs, right? So let's say you have a current source, you need to transform into a voltage source. So therefore, the new voltage source value is equal to Zs times Is. So same with the current source, the new value for the current source. Let's say you have a voltage source over here, you need to transform into a current source. So therefore, the new value for the current source is given by this formula, which is Vs divided by Zs, right? So next, we go straight away to the example. So let's say you are given a circuit, you need to calculate Vx in the circuit using source transformation. So if you look at the circuit, this is where Vx is. So we want to find the value of Vx over here by using a source transformation, right? So by looking into the circuit, right, so we have a voltage source in this circuit, and then this voltage source in series with the 5 ohm resistor. So therefore we know that this voltage source over here can be transformed into a current source. So therefore, in order to do that, right, so uh, we need to transform the voltage source part into a current source part. So this is the new circuit that already transformed to the current source, right? So therefore, voltage source transformed to the current source must be in parallel with the uh, uh, impedance, which is in this case our impedance is 5 ohm. So the value of impedance is not changing, right? So the value of the current is changing. So the new value of the current can be calculated using this formula, which is Is equal to Vs divided by Z, right? So from previous, uh, this is our Vs. So Vs is 20 with the phase shift negative 90 degree divided by 5, right? So this one. So therefore you got Is equal to 4 with a phase angle negative 90 degree, or equal to negative J4 ampere. All right. So if we look again into this circuit, so you can see that the value of Vx that we need to find is over here at 10 ohm. So if you see, this circuit is not simplified yet. So therefore, uh, mm, if you see in this circuit also, you can see 5 ohm is parallel with 3 ohm and J4 ohm over here. So therefore, we can simplify, we can combine these parallel impedance 5 ohm and 3 plus J4 ohm to simplify the circuit. Our purpose is actually to simplify the circuit. So therefore, our calculation can be much easier, right? So therefore, by combining 5 ohm parallel with 3 plus J4 ohm, so this is our Z parallel. So Z's parallel is 5 uh, times 3 plus J4 divided by 5 plus 3 plus J4. So therefore is equal to 2.5 plus J 1.25 ohm, right? So this is the Z's parallel value. So when we combine these parallel impedance, okay, so we can simplify the circuit again. Okay, so the simplified circuit is shown as below. So now you have for current source for with the phase angle negative 90 degree here, parallel with ZP, right? So if you can see from here, okay, this current source is in parallel with ZP. So therefore we can simplify again this circuit by using source transformation, which is, we know that from here you can convert this current source into a voltage source one more times. Okay, our purpose is actually to get a simplified circuit. So therefore, from the simplified circuit, we can transform current source into a voltage source. So this is the new simplified circuit, which is we transform the current source into a voltage source. So therefore, when you transform current source into a voltage source, so your voltage source must be in series with the with the impedance, right? All right. So now we need to find the new value of voltage source over here. So voltage source over here is Vs equal to Is Z's parallel. So Is is 4 with a negative 90 degree angle times Zp is this part, guys, right? This is Zp, which is 2.5 plus J 1.25, right? So by using your calculator, so we got Vs equal to 5 negative J10 volt. So this is the new value for our Vs, right? So if you see this circuit, right? So we can say that this circuit now become all are in series circuit. So this is uh, uh, the simplified circuit, right? So therefore it easy for us to find the value of Vx, right? So we know that in series circuit currents is same throughout the circuit, but the voltage is different for each element. So therefore we can apply voltage divider rules or voltage divided with division to calculate the value of Vx. All right. So hopefully you remember how we use a voltage division. Okay. All right. So from the circuit Vx, this is our Vx, right? So you can find value of Vx by using voltage divider by taking the value of impedance at Vx, which is 10 ohms, divided by total impedance. In this case, all impedance are in series, so therefore you need to do a summation for all the impedance times with your Vs, guys, right? So therefore this is what we get over here. This is voltage resistance at Vx divided by total impedance, right, times your Vs, 5 minus J 10 volt. So therefore by using a calculator, so we get the value of Vx equal to 5.59 with a degree of negative 28 volt. Okay. So this is example for source transformation. So as you know, source transformation, you can repeat this step. Okay. So our aim in a source transformation is actually to get the very simplified circuit, and then therefore the calculation for that we use to get the value that we want is a very simple calculation, right? So either you get, when we say simplify, it simplifies, that's mean either all the circuit become parallel, or either all the circuit become in series, or can be combination parallel and series, mm, as long the circuit is being simplified.